Today's lesson will review some of the techniques that we've just covered in the first few weeks of the course. It will reinforce some undergraduate ideas, and then it will introduce something completely new. And all of that is with respect to bending. The traditional formula that you know and love, sigma x is minus my over I, that has limitations, and the main limitation is that it does in fact work to find the deflection of a beam, but it only finds the deflection of the beam along a specific axis, that is the neutral axis or the centroidal axis of the beam. It doesn't find the displacements anywhere else on the beam. And I don't know if you remember that or even noticed that when you were a sophomore and you learned this formula for the first time. The premise is that plane sections remain plane, so that these lines are all radial lines going to some center of curvature. And that beautiful theory by Euler and the Bernoulli brothers allows for this linear relationship between sigma and epsilon, that profile of compressive stress linearly changing along the height of the beam. The axes are not only the neutral axis, but these axes must be principal axes. And in the Archie department, we do a little experiment where we do unsymmetric bending, the bending of a channel, and you see that it actually moves laterally. It's a fun little experiment that we do in the sophomore year. A principal axis is when y times z times dA is equal to 0, and that is a product of inertia here. If either of the y-axes or the z-axes are axes of symmetry, and by symmetry what I mean that along the cross-section, so looking at this face, if it's symmetric about one axis or the other axis, then this product of inertia will be 0. And later in the course we may or may not look at unsymmetric cross-sections. And then finally there's one more sort of caveat or warning, that the loads are assumed to pass through the shear center. In your steel design classes you probably talked about locating the shear center. That it removes torsional effects on the cross-section. So let's take a look at the shear stress now. If you have transverse loads on the beams, you can have loads going up and down, etc., etc. They of course cause shear forces and in turn cause shear stresses. Quick reminder that the sign convention is not what you're used to from the undergrad, but it is exactly what you're used to in the graduate level class, where a shear stress on the x face must be going up because of the y-axis. So that's a positive shear on this face. What I'm going to do is pull out a green element, but notice where the green element is. It doesn't go all the way down to the neutral axis. It stops before that neutral axis. So I'm going to plop that out. It's a width B, and this face on this side here is dA. So we're going to use the week 1 rules. Remember those week 1 rules? The back face feels the original stress. The front face feels the original stress plus the increment. If you don't know what I'm talking about, go back to week 1. And notice that the bottom of this element starts at y1, and the top of the element starts at h over 2, or c, lowercase c. Or we'll just call it y max. So the bottom of the element is at y1, the top of the element is at y max. Obviously at y equals 0, the stress profile would go to 0. It would hit the neutral axis, but it's a trapezoid here. And the big fun question is, well, I kind of showed you already. If I have stress on this face and I have a different stress on this face, let's assume it's bigger for the moment, how is this thing in equilibrium? How is that element in equilibrium? And notice the increment is partial sigma x partial x times delta x. I'm going over a delta x. And the answer is, of course, that there's a shear on the bottom of the element. There is no shear on the top. You have air. So this is kind of a fun, interesting idea. We'll talk about that in class. And the sigma x's cancel, and all we're left with is that tau is equilibrating this increment. So tau is on b delta x, and remember, it's the bottom face, so that's why it's b delta x. So I'm underneath this green element. That makes it a force here. That's going to the left, so I put a minus sign here. And on the positive axis, I have partial sigma x, partial x delta x, integrating over dA, a little area, and notice the limits. Y is equal to y1 to y equals y max.